Hello guys, how are you doing today? Today I'm gonna talk to you a little bit about internal forces. Right here, internal forces. Internal forces in our syllabus is part of the chapter 7. Chapter 7, or is the beginning of chapter 7. The previous chapter was about trusses, chapter 6. This is chapter 7, it's about internal forces. So let's try to explain what internal forces are, and I'm going to also explain you a couple of preliminary examples about what internal forces are. Usually when I start this discussion in my classroom, I ask my students, have we talked before, previously, this chapter? Have we said anything regarding internal forces? The majority of the students, if they participate, which I force them to, but if they participate, they say, no, never, ever, ever, ever. We haven't done that before. The first time that we heard about internal forces, and we never heard that before. Then I go and I say, okay, do you remember when we studied this chapter, which was just last week or last class? What is this? Oh, this is a truss. Yeah, this is a truss. And we covered two methods for trusses, right? One of the methods was the method of join, yeah. And the other method is the method of section, yeah. So if we do the method of the sections here, for example, and we separate both parts of this truss, then we were gonna find something that it was gonna be like that. And these are gonna be the forces and these members, and in the other side then we will have something like that, etc, 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 and we have that, and these are the reactions, the forces here and the reactions here. We did that, right? Yes. And these forces are subject only to tension and compression. Yes, so you got that part. And those forces are how? Internal. Then yes, we discussed internal forces before. Those are internal forces that happens in the truss, also in the element. And with those internal forces, if we comply everything in the that we have to, all the assumptions and all the conditions that we have to keep, then those forces were only in tension and compression. That was chapter 6, and that was trusses. And those were trusses. So what is the difference now? Well, the difference is, just imagine that now you have an element like this one, aka a beam, and then you have, I don't know, forces, distributed forces, moment if you want to. If you don't want to, it's okay, because these forces are going to generate also moment. And then we have that. And then we want to calculate that the structure. The first thing that we do, or we should do, is calculate the internal forces, the reactions here. If this is the point A, then we have A, Y, A, X, and then we have moment A in, I don't know the direction, but let's say they are like that. Moment A. Okay. If I make a cut over there, and I separate like I did with the truss, I'm gonna separate both parts of that beam. Let's talk about the left part first. So I'm gonna keep this, and this is gonna be like that, with the three reactions that I don't care right now if I know or I don't. I'm just trying to make a point here. And these forces, of course, has a value P1, P2, P3. So this is P1, and as you can see, I'm not in the moment M1 external moment applied there. As you see, I'm not even considering what is that, and I don't care about that. So this is here P2, for example. This is P3. This is M1. And let's say that I select this part because I know in the truss I have internal forces that compensate and keep in equilibrium every single one of the parts of that truss. Now if I make this cut in this beam, I know for sure there have to be internal forces here to keep this in equilibrium. How do I know what internal forces are produced here? Okay, let's try what is happening here. Let's do summation of moment of forces in X, that means that there has to be a force in X here, an internal force in that direction in X, in order for this to be 0, because I have a force here and I have a component here also, and I'm gonna have this force here. This force is called N, or is called A, and this is called axial force or normal force. I don't like using normal at this level. This is more like for physics. Why is called normal? Because that force is perpendicular to the cross-sectional area. And what is axial? Because go through the axis of the section, which in most of the cases is the neutral axis or the centroid, depending on if the situation that we are working with. Now, for doing equilibrium in Y, then I have to have also a force in Y, an internal force in Y. That internal force in Y is called shear force, and I'm gonna write it here because my students always make fun of my accent. Shear force over there. And also I had that for shear, that shear force over there, but at the same time, if I do summation of moments here, it has to be 0, and I can guarantee you that most definitely if you do summation of forces and you put everything there, an internal moment is going to be required also here in order to keep that in equilibrium. So for summation of forces in X, there is an axial force that should be appearing there. Summation of forces in Y, we should have a shear force, and summation of forces, summation of moments at that point, we should have a moment, an internal moment over there. Now, why these forces are important and what those forces are used for? Well, of course, if in this part I have these forces at this other end, because it's the same point, action reaction, then I should have an axial force, I should have a shear force, and I have a moment opposite to this direction. By the way, I always said it doesn't matter what is the convention that you use if you state your convention. That means that if you're gonna do summation of forces in X equals 0 and then you select this to be positive, that's perfect. If you say summation of forces in Y equals 0 and then you select this to be positive, that's perfect. Summation of moments equals 0 and then you say this is positive, perfect. I don't care about that. This convention, you should keep this convention. These are the positive direction for the shear, axial, and moment if I use this section of the beam, and this is the positive direction for shear, axial, and moment if I use this other section of the beam. Always is going to be like that. Can I use a different convention? Yes, but this is the generally accepted convention, and mostly every single textbook that you're going to study are going to consider these values as positive. Oh, but that force is pointing down, that should be negative. That has nothing to do with this. This is a convention that I'm using for making this equal to 0. If I say up or down, it's the same thing. It doesn't matter, it's equal to 0. It's like getting the equation of multiplied by -1. You know, you're gonna see exactly what I'm meaning with that. Now, where do you think you are interested in calculating those beams? For example, I don't know. When I go to this part, I always like to tell my students what for you are going to use what you are learning, because I think that once you know what you are doing, it helps you to understand a little bit more about why you do and what is the importance of what you're doing. So let's say that you are you are designing reinforced concrete beam, a reinforced concrete beam. A reinforced concrete beam is a beam, of course, made out of concrete, and I'm pretty sure you have seen it. You have something like that, supported here and supported there. For example, this material is concrete, and usually when I teach also I say, oh, what is concrete? And somebody says cement. No, concrete is not cement. Oh, it's cement plus water. No, it's not cement. Oh, concrete is something that they sold in packs in the hardware store. Well, yeah, they sell it in those sacks, but this is not concrete. What is the definition for concrete? And then this is topic for another lecture, but anyway, concrete is just a mixture of cement, of course, coarse aggregate, which could be crushed stone, and you have also fine aggregate, which most of the time is sand, water, and in some cases you have admixtures. And why do you do that? Because actually what you are creating when you create concrete is an artificial stone. So that should be the definition of concrete. It's an artificial stone or an artificial rock that you are creating based on the combination in appropriate ratios of those materials that I told you. So what is important about this? Because it's reinforced concrete. Reinforced concrete. What means reinforced? Oh, because it's not only concrete. You have some steel rebars, and those steel rebars go usually here and at the top also. And on top of those steel rebars, then you have a bunch of other rebars also in this way, that they go all the way from end to end, and they are closer here, and they are more spaced at the center, and these are called stirrups, but there's also steel rebars. And why I'm talking about this, because look, whenever you have for example any beam, and that beam is subject to a vertical load like that, or a perpendicular load. It could be distributed load, it could be concentrated load, it doesn't matter. But that beam is gonna try to deflect something like that, and it's gonna bend like that. And I always tell my students, of course I'm exaggerating it here, and I always tell my students, okay, imagine that beam is made out of Play-Doh, plastiline, clay, rubber, and you get that beam over there, and then you do this in that beam. And I'm gonna use something that I found here in my office. This little bus that I have here is made out of foam, but it's gonna help me to explain you what is here with that beam. So if you have this beam, and I apply the load here, that's what's gonna happen to that beam, right? Exactly what I'm saying there. Now look what happened in the top part of that beam. The top part of that beam, when I do that, you should be able to see what is happening there. You should be able to see what is happening there. You see a bunch of wrinkles that are happening here in this area. That part is getting wrinkled. The bottom part, it should be if this is made out of a more brittle material, you could start seeing cracks here in this part. So wrinkles here, cracks at the bottom. Why is that? Because the fibers of the material are getting compressed against each other here. That's why you see the wrinkles that you see. And why they are getting compressed? Because this is exactly the behavior that is happening here. So the top part of this beam under these circumstances is subject to compression, and the bottom part is going to be subject to tension. If you make a cross-sectional view of this beam or of that beam, I'm going to make a cross-sectional view of this. This part should be in compression, and this part should be in tension. And I know this is not static, guys, and if you don't want to see this, it's okay. You just have to fast forward the tape. But I consider this important once again. So if this is your beam, and this is compression, and this is tension, because this is going to set the mood for everything else in your engineering class or classes. If the top part is subject to compression, that means that originally you have a length, and that length is getting reduced, and in this part, so this length is going to be smaller, this part is going to be smaller in the top, and this part is going to be bigger here. If this is in compression, you're going to have a deformation probably in compression, I don't know, I'm gonna put compression here and tension here. It's gonna be something like that. Compression and tension that is not elastic. This is the deformation, the strain is not elastic. But let's say that for the sake of this discussion, this is elastic. There's something that it was modified because the stress here, you know, there's a stress and there's a strain and there is a stress also, and there is a relation between a stress and a strain, and you will learn this later in mechanics of material. It should be something like more like this in this part, but it doesn't matter. It was idealized like something like that, where this is also a block in compression, and here this part is in tension. Now what is important once again about the reinforced concrete is that the concrete is a material that is very good for resisting compression. Very good for resisting compression, meaning, I don't know, maybe 5 ksi to 6 ksi are normal values for concrete. 4 ksi, 5 ksi. 6 ksi means 6,000 pounds per square inch. That's a lot. That's a lot. Why is that a lot? Well, imagine what I'm telling you is 1 inch by 1 inch. This is the area, and on top of that I'm putting 6,000 pounds, 3 Volkswagen cars, for example, on top of this. That's the value that or a typical value for the concrete to resist in compression. That's a lot. That's a lot, I'm sorry. A little cube like that with 6 Volkswagens on top of that, for example, 6 2,000 pound car, 3 2,000 pound car on top of that, and the block is still resisting that. However, in tension, that material, let's talk about maybe 10%, 600 pounds per square inch, which is still something, but not that much. Now in the top part, as you remember, it was compression. In the bottom part, it was tension. So this part, the concrete is able to resist it perfectly, that compression that is happening here. But in the bottom part, at the bottom part, the concrete is going to start cracking everywhere in this part. And what the theory in reinforced concrete applies is that if the concrete is cracked, it's not working, or well, it's partially working, but this is statics. I don't want to overcomplicate it. So the concrete is not going to be able to resist that tension force, tensile force that is coming from here, and then that's why you have the rebars of steel, because the steel is really good at resisting tension and is providing this tension in this part. Now, why I'm explaining you all of this? Well, I'm explaining you all of this because I just want to show you that you know more than you think you know already. Look, if you do summation of forces in x direction here, C has to be equal to T. And you know that because summation of forces in x. Now, if you calculate the moment, those are internal forces here. Now, if you calculate the moment produced by these two forces, this is a couple multiplied by this distance, which is called JD in concrete, but it doesn't matter, it's a distance, no matter what. That force multiplied by this distance JD is going to produce an internal moment. That internal moment is the one that is going to absorb the moment generated by the loads. This internal moment here, this internal moment, which is coming from all the external forces at that and moments at that point, that is the way the reinforced concrete, for example, absorb that moment. Meaning the longitudinal rebars, or these rebars, are designed with the moment. Now, another question that I ask all the time is where should we calculate that moment? Where should we calculate that moment? And this is just a really quick presentation. It's only one slide. It's not even a presentation, but I was just telling you this. You see, when I apply the force, the top part is subject to compression, the bottom part is subject to tension, And if it's reinforced concrete, then you're going to have the element like that. These are going to be the bars that I'm designing with the moment, and also you have bars here on top. That's another topic, and we will discuss that maybe in the future if I teach you reinforced concrete. And these are the stirrups. So these longitudinal bars are designed with the moment, with that moment, that internal moment that you calculate over there. And the other question that I say is where do you think is the most critical part, the most important part? Where do you think I should design that moment? Where do you think I should calculate that internal moment? Where do you think I should calculate this internal moment here? And usually people say, oh, at the center, because the center is the moment is going to be bigger, and I know that because it's something out of logic. The deflection is going to be bigger, showing that probably the moment is bigger there. Yes, at the center is, in this case, is going to be the biggest one. But that doesn't mean that I only calculate at that center. I have to calculate the moment everywhere, at every single one of the points, because I'm designing every single one of those points. What does that mean? Well, that means that I need to know the moment everywhere. That means that I have to get this section, for example, and I start section, infinite amount of section. Oh my God, that's too much work. I agree. But hopefully, or thankfully, there are some methods that we can use for that allows us to draw some diagrams. What diagrams? Well, I'm gonna do shear diagram, I'm gonna do moment diagram, and I'm gonna do axial or normal diagrams also. These diagrams, basically I have to do 2, 3, or 4 sections, and then I'm gonna show you later in a video how to do these diagrams and how we can, only with doing 2 or 3 or 4 different sections, similar to that, or similar, some interesting points over there, we can draw these diagrams, which is going to tell us the behavior of the internal forces everywhere in that beam. Okay, now that's the moment. I know what the moment is used. In this case, for example, the moment is used for designing those rebars, because I need to know the stress. And remember that word, stress. You use that word a lot and you don't know what stress is. If I was you, I will go and I will investigate what stress is before even saying stress or strain. What about the shear? What about the shear force? Well, you know something, shear is a force that is trying to cut the beam. It's trying to cut it. That's why these elements here, these elements here, these elements here, the stirrups, are exactly designed for avoiding that cut to happen. So you use the shear, for example, in this case, to design that, and also the cross-sectional area, because you have to cut all the section. If you're gonna cut it in half transversally, the section is also gonna be able to absorb that shear. And finally, you have the axial force. What force do I use the axial force? Well, you use the axial force for several things. One of the things that you use the axial force is for designing the cross-sectional area also. And do I have axial forces in beams? Yes, you do have axial forces in beams. Of course, predominantly you have vertical forces and moments, or vertical forces, or transverse, not vertical, transverse forces. But now this is a beam, perfectly. Now if you consider this like that, now it's a column. And yes, you do have axial forces. And what is absorbing this axial force? The cross-sectional area and the steel rebars also. This is the part that is absorbing. So this is why basically you need to know and you need to calculate those internal forces. And I'm just pulling an example out of reinforced concrete because I love reinforced concrete. But this could be everywhere, anywhere, any material. Any material, you have to know the internal moment, the internal shear, and the internal axial force, because those are the ones that are gonna make you for the section, for the material, for the cross-sectional area, for everything else. Now remember, I do this by doing those shear, moment, and axial diagrams, and there are several ways for us to do that, several methods, and we're going to be working with those methods. The first method is called the method of the sections. The second method is, what is the method of the sections? Duh. The method of the section is doing sections, like we did that, and doing summation of forces x, y, and a moment at every point in every section that you need to do. Then you have another method, which is the method of the integrals. And you have another method, which is called the method of the areas. And these two are very interrelated. But we will do this later, and I will explain this later to you. Right now, I want to introduce a couple of examples in how to calculate the internal forces. And when I say forces, I include the moment. Internal forces, for me, is going to be internal forces all the time. It's going to be axial, shear, and moment. When I talk about internal forces, I refer to the three of them. Oh, but the moment is not a force. I know. That's what I'm doing this disclaimer. For me, internal forces is going to be axial, shear, and moment. So let's do an example to try to show you how these internal forces are calculated by the method of the sections, and how you are going to work with that. This is a simple example, and let me see, what is this? Okay, first, you have a beam like this, simple support here, and a roller in this part. A simple support, I mean a pin, and then you have a force of 8 kip there, and you have these distances. This is 8 feet, 8 feet, and 8 feet, and this is the point C, this is the point D, this is the point A, this is the point B, and there is also an applied moment here of 40 kip per foot at this end. And the question that we are asked is, calculate the axial force, the shear force, and the moment at the points C and at the point D. We have to calculate axial shear moment at the point C and D. How do we do that? Well, the method that we're gonna use is the method of the sections, because this is the method that I'm introducing right now, method of the sections. And as you know, the method of the sections, what it tells you is just to make cuts at those points. Now, first of all, do you know what a kip is? You should know what a kip is. But if you don't know what a kip is, 1 kip is equal to 1,000. That's where the K comes from. And this P comes from pounds. So 1,000 pounds. That's what 1 kip is. And why pounds? Why P? Because that comes from Latin. You know, pounds is English, but LB is Latin and comes from Libra in Latin, but that's another thing. So kilo, pound, basically kilo, Libra, or KLB. Okay, that's one of the first things. The other thing that people always ask is, how can I have a concentrated moment of 40 kip there? If this is a roller, the roller is not going to be able to resist any moment. Who told you the roller is resisting moment? The combination roller, pin, those are the ones resisting moment, not the roller itself. So how this moment could be applied there, I don't know. Maybe it was another beam in this point, and that beam was subject to torque, and that was producing that moment over there. Maybe, and just maybe, I have something here like that, part welded here, I don't know, with a force like this and with force like that, couple, and that produces that moment. I'm beyond that point now. Somebody simplified that situation for me and gave me that moment. That's the only thing that I care. So the first thing first, we have this problem and we have to solve that problem. There you go. Reactions. AY, this is a pin. AX, this is a roller. BY. Those are my reactions. We start by calculating the reactions. How do we calculate the reactions? Calculate reactions. How do we calculate reactions? Summation of forces in X equals 0. Of course, first step would be, is this statically determinate or indeterminate? Well, it's statics, right? So determinate. But anyway, summation of forces in X equals 0. AX, anything else? No, 0. AX is 0. If this force was inclined, then I will have a component in that direction that will make that not 0. Summation of forces in Y is going to give me AY and BY as unknown. So let's do summation of moments at A equals 0. I'm going to say this is positive. Oh, wait a second, but you just say something about it. Yeah, that's convention for internal forces, not for summation of forces. That's different. Here, I assume anything that I want to assume, and I stated it. Summation of moments at A equals 0. Okay, good. Now I'm going to apply this force here, so it's going to be 8 times 8, and it's going to rotate in this way. And that is negative according to my convention, negative 8 times 8. This moment here is applied already. That's a positive moment according to this convention of 40 kip. And then this force here is going to be 8, 16, 24, 24 times By, and that's going to be a moment that is going to be according to whatever assume also positive, and that's going to be equals 0. And then when I solve for this, then AY is going to be BY, I'm sorry, BY is going to be equals to 1 kip. 1 kip. This is what? This is 40, and this is 64. So that means a negative 24 passes to the other side positive. Yeah, it's going to be equal to 1 kip. 1 kip. Summation of forces in Y equals 0. Then I have AY minus 8 plus BY, but BY is 1 equals 0. Negative 7 plus 1, negative 7 passes to the other side. Positive AY equals 7 kip. Good. I have my reactions in X, Y, and I don't have any moment reaction because this is a pin support and this is a roller. Now the next thing that I want to do is calculating my section, because it's at the point C. That means that I have to make a section there, and I'm going to make a section at that point. I'm going to make a section at that point. This is the point C. This is my reaction, 7 kip. I'm going to put it like that. AX, I'm not even going to put it because I know it's 0, so I don't want to complicate the drawing if I don't have to. And this is the point A, this is the point C, and at the point C, if you remember when we were discussing before, somewhere over here, I told you that immediately these 3 forces, as soon as I make a section there, these 3 forces are going to show. So look at the convention of the forces. This is important. I'm going to put there this force, and I'm going to call it V sub C. This moment M sub C, and this axial force in this direction A sub C. Those are my 3 internal forces, and this is the positive convention for those internal forces. Now this distance here was 8, meaning this distance here is going to be at exactly at the point C. It's going to be 8 feet. And I'm gonna do it like that. Now, what happened at this point? There are 3 options, I will say, and I always say this in my classes, and we have a discussion about this in my classes, and I say, okay, I'm gonna make that section, but look what happened. I have a force on top of that. Should I include the force, or shouldn't I include the force? Who says should I include the force? Think. Give me a good reason for that. There are people that say, yes, you have to include the force in the section because then the force is going to be there, and that force is going to be producing something in that section and it's part of the beam, so you should include that. Yes, you're right. There are people that say, oh, wait a second, that force shouldn't be there because if I just cut it a little bit before the point, that force is going to be in the other side of the beam, and whatever is happening to that force is already included in the reaction. Yes, you're right. And there are people that say, oh, you know something, I'm gonna use the Solomonic rule here, Solomon rule. I'm gonna cut it. So if that force is 8, I'm gonna put half of the force in this side of 4 kip, and in the other side I'm gonna put the other half of the force here of 4 kip. Well, if this is your theory, you are the one that did it wrong. But if you include it and you did this and you say, no, I'm going to put the force of 8 kip there, and then in this side I'm not gonna put the force, that is correct. And if you say, no, I'm not gonna put the force here, but I'm gonna put the force in this other side of 8 kip, of course here I have my reactions, I'm not putting the reactions, but that is also, and of course here in every point I'm gonna have my forces also, and here remember 1, 2, 3, and then I'm gonna have the other reaction here, the shear force, the axial force, and the moment, like that. This is correct, this is correct. Oh, wait a second, but if I calculate the internal forces here, these values internal forces are gonna be different than these values internal forces. You know something? That is also correct. So how come everything can be correct? Well, let's see it. Let's start the first part of the problem. And for the first part of the problem, I'm going to let's say that I'm not going to include the force of 8 kip. I'm not going to include it. I'm just going to do it like that. So if I don't include that, that means that my section is not going to be 8 feet the distance, but that distance is going to be a little bit smaller than 8 feet. A differential smaller than 8 feet, if you will, if you want to see it like that. Then that means that in this other end, at this other end, when I have these 40, this is 1, then the force is going to be applied here, like that. And then this V will be opposite to this one. I'm not going to put the axial because we already know it's 0, and this moment is going to be opposite to this one. This is the first situation, when my section is between A and C but not touching the point C. Okay, if I do that, I'm going to use this part. Why? I don't know, because I think it's easier than this one. I could use any, but I'm going to use this part. And then I'm going to say in this part, summation of forces in x equals 0 means A is 0. We knew that. There's nothing happening in x, so this force is 0. Now I'm going to say summation of forces in y equals 0. And if we do summation of forces in y, then I have 7 minus VC equals 0. VC equals 7 kip. Wait a second. What are you doing here? So you are telling me that this is a positive convention, however you are putting this negative sign here? Yes, that's exactly what I'm doing. And try not to overthink this, and listen what I'm telling you. Yes, this is the positive convention for VZ. What does that mean is that when I do, remember what I told you, summation of forces in y equals 0, I don't care about what I assume positive or what I assume positive. I don't care about that. In this case, I assume this positive, right? Because it's equal to 0. What is important is that at the end, when I put my force like that, if the value that I get here is positive, that means that the internal shear is a positive value. That's what I mean. Remember tension, compression, whatever, entering the joint, leaving the joint in trusses? Okay, for this case, whatever, if I assume my positive direction like that, and at the end I get a positive sign here, what does that mean is that that was positive, that internal shear. You will see this later, don't worry. And then you do summation of moments, and the easiest way for me to do it always is at that point at the point C, and I'm saying this is positive, so if I do moment there, I'm gonna have 7 times 8, and it's gonna be like that, negative 7 times 8 plus MC equals 0. That means that MC is equal to 56 kip foot. There you go. Positive also, because I put it in the positive direction and I came out with a positive value for moment. Now this is the first part. Now let's keep going with the same problem. But in the same problem now, I'm going to make the section between, let's say, a little bit bigger than 8 feet. So to the right of the point C. If I make the section to the right of the point C, that means that the point C is here and the force is there. So the force is past, the section is past the force, so the force is going to be acting there. This is my 8 kip force in this side. This is my 7 kip reaction, and this distance is still now 8 feet. And if you are one of those mathematicians that argue this is not 8 feet, okay, 8 feet plus the differential of distance, 8 feet in layman terms. And then you put here your forces again, VC, MC, and your axial force. I'm not going to put the axial force because I know what is happening here already. Summation of forces in X equals 0, axial is 0. I'm just going to keep it like that. And I'm going to do again, summation of forces in Y equals 0. Now what do you have here? You have 7 kip minus VC minus 8 equals 0. That means that VC is going to be 7 minus 8 is negative 1. Pass this to the other side, negative 1 kip. You see, I put it in the positive direction and I got a negative sign. That means that after that point, the shear force is going to be negative. And why do I care about positive or negative? Remember the zeros that I was telling you? Remember that part? That's important for that design. Now, summation of moments at C equals 0. I'm going to use this. And then I have 7 times here, right? 7 times 8. 7 times 8, and it's negative in this way. And I have plus MC equals 0. So MC equals 56 kip foot. And now let's take a moment here and let's see what is happening. My original beam is this one. This is my original beam. And I say, let me calculate my internal forces before the force and after the force. And let's see what happened. We calculated the internal force before the application of the force, before this point, and then we calculated immediately after that point. In one case was 7, and in the other case was negative 1. Now, if you think, and this is your beam, and you have a force here, that force is trying to cut this beam with the magnitude of 8 kip here. Now remember what I have here. My reaction here was 7 kip at this end, 7 kip, 7 kip, and then suddenly I find that force of 8 kip acting here. Just before that force acted, my internal force has to be equal to this 7 kip. That's what is happening here. Just before that point happened, my internal force should be equal to that, but immediately after that point, that force is acting and affecting my 7 kip originally, and it's giving me a residual 1 kip in that direction, or in the other direction, negative, in the other direction. The total jump between this condition of 7 kip and this condition of negative 1 kip, the distance between this value and this value, if you will, is 8 kip. That's the value exactly of the concentrated force applied on top of that. The moment, however, didn't change. Why is that? Well, I know this is early for that, but I'm just gonna introduce you to the don't worry if you don't understand what I'm telling you right now. But when we do the shear moment diagram, at that point, what is happening is that this is the shear diagram. I'm gonna put two horizontal lines here, and I'm gonna draw the shear diagram here. You'll understand this later, but I'm just gonna show you what happened here. This part is the axial force, so the axial force is gonna come like this. This part is gonna go up, and it's 7. The value of the reaction was 7. This is gonna be constant up to this point. I find this 8. I'm gonna come here, and this is -1, and this is gonna be constant up to this point and ends here. You see this value here before the point C, 7. After the point C, -1. That is what's gonna happen there. And when you do the moment for this, the moment for this will be 7 times 8 is 56, so it's going to be something like that, 56, and it's going to continue with this 56 here in this direction, 56, 7 times 6, 56, and this is 8 and 7, 16, 7, it's going to be something like here, here, and this is positive, actually it's negative, like that. This value here is 7 times 6 is 56, and from here it's going to continue because there's nothing that makes me change it, and this is -1 times 6 times 16. This is 16 here, 16 up to this point, and then it's going to close like that. That's what's going to happen there. That's what's going to happen here, and it's going to close here. But the moment, when I draw the moment, and don't worry about this, okay, when I draw the moment here, at that point the shear changes from 7 to -1, and the moment didn't change. Now, if you don't understand this right now, it's perfect, unless you know a little bit of this. But what I want you to put in your mind right now is the following. Whenever I have a concentrated force acting at a point, the shear diagram is going to jump in the same direction of the force, in the same value of the force. That's what happens here. And the moment is not going to change at that point. Put that in your head, because that's going to help you with this one. What happened, just a really quick checkup before finishing this part of the video. What happened if I decided to go with this side of the beam instead of using that side of the beam? I could have done that, no problem. I can say summation of forces in Y equals 0. And then I have VC minus 8 plus 1 equals 0. How much is VC? VC equals -7. 7. What is the value that we got before? 7. The same situation. Nothing happened. And if I use this part here and I say, oh, let me use the other side, do it and compare it. Now, in your textbook, usually you are not going to have the problem that do it before and after, because the books usually are going to tell you, calculate the internal force. If it's only internal forces, the problem is going to tell you, calculate the internal force at the point C, and then they are going to tell you, consider that the point C is to the left of the force. Then you don't include the force, because if the point C is to the left of the force, you don't include the force. Or if they tell you, consider that the force is applied to the left of the point C, oh, then you have to consider it, because they are telling you, here's the point, and to the left of the point C is the force. So then I have to consider the force. What about the point D? The point D, you only do it once, because you don't have a concentrated force. You only do it once, and that's your job, so you're gonna do that, and you're gonna calculate that for later. In the next video, I'm gonna show you a typical example like this, but with a concentrated moment and with something else. So see you next time, guys. I hope that you enjoyed this video. I'm sorry because I took a lot of time for explaining you something about real life and how the reinforced concrete works, but on the other hand, I'm not sorry. That's what the professor is supposed to do, explaining you what and why you are going to use what he's explaining you. See you next time.